Hello, everyone. Good morning, good afternoon. Thanks for joining this LoRaWAN webinar on the LoRaWAN Protocol, LoRaWAN Protocol 101. So basics, introductory talk. So I am Olivier, the technical committee chair, the LoRaWAN technical committee chair, and I work for Semtech as a technical fellow. So I am a technical guy, obviously. Before we start, let's review some housekeeping notes. So you may submit your questions at any time during the presentation, and I will answer them at the end during the Q&A part. We record this session, and it will be available on demand along with the slides, so you don't need to take screenshots. If you experience issues, try refreshing Zoom. That can work. And also you can find more resources in the Zoom tool. So let's start. What problem are we solving with LoRaWAN? So we are dealing with IoT, Internet of Things. So this is about connectivity for things and sensors, and also sensors attached to things or machines. So for the connectivity part, we need wireless coverage, wide wireless coverage, using a minimum infrastructure because we want to keep the cost minimum for small things and sensors. So therefore, we need long range. We also need to address battery-operated devices or devices which operate out of energy harvesting, meaning harvesting light, vibration, temperature difference to remove batteries. So we need, for all that, low power operation on the end devices. And last, we need a protocol which is tailored for low data rate, and more specifically, infrequent short transmission from or to the end devices. So it's also important to acknowledge what we do not need to solve with LoRaWAN. We do not need to go for high data rate that reduced the cost per transmitted byte, because even though the transmission are short, there is value in every piece of information, in every bit that are transmitted by the sensors. Probably the sensors are the one where the value per bit is the highest compared to broadband internet, for instance. We also do not need to solve for capacity because coverage is a hard problem. Wireless coverage is a hard problem that we don't completely solve with LoRaWAN, and that no technology is able to solve anyway. But it's such a hard problem that when you cover a given area, you have plenty of capacity for IoT, for things and sensors. So the problem is getting long range, so low cost coverage, low power, and a protocol optimized for low data rate of the sensors. So that's what we solve with LoRaWAN. This is how we solve it. We solve it as an alliance, as the LoRa Alliance. So we are the LoRa Alliance, and what we are is technically a global open non-profit organization launched 10 years ago. But what we are truly is an innovation ecosystem where partners collaborate on technical standards definition. Then they compete on the market, they make their own business decision, but we collaborate to define standards and interfaces, standard interfaces. So we develop these standards, and that's the main role of the technical committee that I'm chairing. So if you want to do technical things in LoRaWAN, please join the TC or join any task force under the TC. Any member can join the task forces. So the LoRa Alliance is recognized by the ITU as an official international standard. Our LoRaWAN spec has been transposed into an ITU recommendation, an ITU-T recommendation. We also educate the market about the LoRaWAN technology, its latest advancements, and its active deployment. So education is what we are doing right now, today. And last but not least, we develop and maintain a certification program which allows device manufacturers to put the LoRaWAN certified mark on the devices, but more importantly, which ensures interoperability between any LoRaWAN network and any certified device. So again, if you want to contribute to any of this or stay up to date, consider joining the Alliance. Another thing we do as an Alliance is making LoRaWAN accessible, making it really ready to use. So either for end device manufacturers or application or solution makers. So if you're an end device manufacturer, you have access to a LoRaWAN reference stack, which is an open source implementation of the protocol on the end device side. This reference stack is, of course, aligned with the spec and passes the certification program. And there is a specific certification testing tool that we call the LCTT, which is essentially a network emulator that checks that everything works on the end device side. So you take the reference stack, you modify things you need to modify because you need to run an application on top of it, and then you verify with the LCTT that your device is going to be certified. And then you go for the certification program. You can even go for a self-certification. That's a possibility that we opened recently. So on the application and solution maker side, if you want to build and use LoRaWAN, well, you can use LoRaWAN certified devices, which are guaranteed to work. And then you have several network options, public network operators, which are present in most countries in the world, or you can set up your own network, make a private network dedicated to one application or dedicated to a few applications or dedicated to a place. And we have community networks, which is a way of collaborating between people that have small localized private networks, but which are all interconnected together, making a big network. If you don't want to go to the route of buying sensors and buying subscription or getting network yourself, you can go to system integrators up to sensing as a service. SaaS stands for sensing as a service, which is in a way the ultimate integration, because there you pay, you subscribe to data, and you don't even know that there is a sensor, a network, and a protocol between the sensors and the network. So LoRaWAN is ready to use, but that's not a reason not to dig into how the protocol works, and that's what we're going to do today. So today, I will maybe scratch the surface of the LoRaWAN protocol by addressing first the difference between LoRa and LoRaWAN, then show how power efficient the protocol is and why it is power efficient, what are the design choices that make it power efficient, what are the reasons that make also LoRaWAN state of the art when it comes to security, and then I'll talk about coverage, which is one of the main advantages of collaborative network topology that I will detail, and also talk about coverage expansions. So let's start with LoRa versus LoRaWAN. So LoRa is a radio modulation for point-to-point communication between two devices. It has two and a half very important properties: long range, low power, and the 2.5 is the instant signal detection. That comes with low power, but it's really very important. So it's actually a property on its own. So for the range, the range record today with a small power of 25 milliwatt, 14 dBm, is more than 1,000 kilometers. So that pure range in pure line of sight, that's not very interesting. That's good for records, but what it means practically is that in a rural scenario, you can get up to 15 kilometers range, and in an urban scenario, up to 5 kilometers range. On the low power side, first of all, the transmit power is low. One of the reasons is that LoRa is a constant envelope modulation, meaning the amplitude of the signal is kept constant throughout any transmission. That allows an efficient use of the radio power amplifiers. Typically, the efficiency of a radio power amplifier is around 50%, meaning that 50% of what you want to transmit in what is transmitted as radio waves, the same amount of what is transmitted as radio wave is dissipated in heat in the power amplifier, and this is the dominant part of the power consumption. So having, and if you don't have a constant envelope modulation, the power efficiency goes down maybe sometimes to 10%. So 50% is a good number. Also on the receiver side, the reception complexity is very low. That allows, by the way, to have simple gateways, but that also allows to have very low complexity, therefore low power receivers. So the transmitter is low power, the receiver is low power. Therefore, the bidirectional link is low power. And last but not least, we have this instant signal detection property, which allows for asynchronous reception. So this property means whenever a receiver is actively looking for signals, so it's actively receiving, whenever it's actively listening to the channel, if there is a signal, it will detect it instantly, well, with a very short delay. There's no need to synchronize in frequency. There's no need to synchronize in code phase. So it's completely asynchronous. And this property will be used in several places by the protocol, by the LoRaWAN protocol. So LoRaWAN is a radio network standard for point to multipoint and interoperable networks, scalable networks between many end devices and gateways. So it uses LoRa as a physical layer for range and low power operation of the end devices. LoRaWAN uses sub-gigahertz unlicensed spectrum, which frequency vary with region. The North America, South America, Europe, and Asia typically don't use the same frequencies. The very important property of a LoRaWAN network is that there is collaborative reception from the gateways, and I'll detail that later. This is much related to low power of operation and ease of deployment. And the protocol itself only happens 13 bytes per message. That's a way to optimize the overhead of the protocol. In addition to this only 13 bytes for each message, there is a constant connection to a network, and the device transmits and receives instantly without prior synchronization or authorization to transmit or receive, which means that the signaling on the network is very low. So this protocol is already very successful, as you can imagine. We have more than 100 million deployed end devices using the LoRaWAN technology. This is from 518 devices which have been certified. So, and it's possible to certify a device for multiple regions, which is why in total we have 868 certifications. So some devices are certified for, say, North America, Europe, and some others for the three main regions, Americas, Europe, and Asia. But yeah, and some devices are only certified for a single region. This is growing fast. We don't have the exact numbers because most of the deployments are private networks, small private networks. But if we look at the biggest deployments, the 4 or 5 biggest deployments total around 20 to 25 million end devices and experience growth between 25 and 50%, depending on the vertical they address. So it's big already and it's growing pretty fast. Here is the technical architecture of LoRaWAN. So we have end devices, gateways connected to end devices. Well, actually, they're not really connected to end devices. They relay messages from and to the end devices. And what the end devices are really connected to is a network, which is a set of 3 main servers, a network server, a joint server, and an application server. And at the output or input of this network, there is application data from and to the end devices. The role of the joint server is to share secrets with each device. We'll see that with the joint procedure, during which the joint server authenticates the device, and the joint server also distributes the session keys. So the joint server is really the root of security, the root of trust in the LoRaWAN network. The network server, the LoRaWAN network server, controls the gateways, manages the device, and exchanges traffic with other network server whenever it needs to, if 2 network servers or 2 or more network servers need to collaborate to increase the coverage using the different gateways they manage. And at the end of the network, at the south part of the network, lies the application server, which encrypts or decrypts the application data and also transform this application data according to payload codec. The LoRa Alliance standardizes the interface to such payload codecs, so coder, decoders. Security now. Security relies on AES-128 primitives, 128 primitives, which is a very well-known set of a very well-known set of primitives. So the cipher suite we use uses these primitives in a well-known, in the normal way, in a secured way. So that's why the LoRaWAN protocol by itself is designed to be secure. We are adding cipher suite agility in LoRaWAN version 1.2.0, so the upcoming release of the LoRaWAN protocol. For instance, it will be possible to initiate a session using AES-256. So AES-128 is perfectly secure, but some markets require AES-256 probably to be safe for 20, 30 years versus possible post-quantum cryptographic attacks. But for now and for the years to come, or the tens of years to come, AES-128 is good enough and considered completely secure. But we have some markets that require AES-256. There are also other markets which require different primitives than AES-128 or 256. So that's for the protocol. The protocol by design is secure because we reuse state-of-the-art security implemented by AES-128 primitives. The second level is to verify that implementation of the protocol is correct. And that's the role of certification. Certification ensures that the implementation of the protocol is correct. And then the last stage is to make good deployment, to deploy with care for security. And for that, we recommend, of course, we cannot check everything that the network operators or the users do, but we do recommendation for secure deployments. And if people follow this recommendation, their deployments will be perfectly secure. The security of LoRaWAN of a session starts or is renewed with the join procedure. And now I'm going to explain, to detail what the join procedure is about. So we have this network that we've seen already with devices, gateways, network server, join server, application server, and there's a new device coming in. We suppose that this new device is here. This device is identified with a globally unique identifier that we call the device EUI. This dev EUI is so again globally unique ID allocated by the IEEE. So a device manufacturer needs to acquire numbers, globally unique numbers by the IEEE. And this identity is linked to a secret key, which is present in the device and also in the joint server. So the joint server really acts as a safe for identity key pairs for all devices. So the joint server knows the identity and the root key of each device that is in the network, or each device that may join the network. So the device wants to join the network. So and only the joint server knows the root key. Only the joint server and the device know this root key. Whenever the device wants to join or rejoin or reestablish the session with the network, it will send a join request that will be forwarded by a gateway, any gateway, then will be forwarded by the network server to the join server. There is the identity of the join server in the join request, so it's the network can route the request to the right join server if there are several join servers. Because the join server has a copy of that key, it is able to authenticate the origin of the join request and make sure that this device made that join request. Because it has authenticated the join request, it can send back a join accept message, which is also protected and signed by this root key. So the device verifies that the join server also shares with it this red root key. With the root key, information contained in a join request and information contained in join accept, two session keys, one network session key, which is here in yellow, and one application session key are derived. Key derivation is a one-way process. If you know that key, you cannot go back to the root key and you cannot go to the other session keys. So there is complete isolation going up or going on the sides. So that's a way. It's a way to keep things secure, because once the session is established, only these session keys are used. The join server provides the network session key to the network server and the application session key to the application server. This application session key will be used for end-to-end payload encryption, because only the end device and the application server use and know that key. And the network server will use the key for protecting the good operation of the network. So making sure that the origin of frames is that the frames are legitimate, that they come from end device on the network, verify that the frames have not been modified, so this is integrity protection, and verify that the frames have not been replayed. This is protection against replay. How is this working on a frame level, frame by frame level? So in yellow is the protocol overhead that is added to each frame, and in green is the payload. The applicative payload is always encrypted using this application session key. So that part is encrypted using the green key. The message integrity check, or MIC, which is at the end of every LoRaWAN frame, is computed with the network session key. So it can be computed and by the network server, verified by the end device, or computed by the end device and verified by the network server. And it proves the origin of the frame, because only the owner of the key can compute the message, the MIC. It protects the integrity of the message, because if any bit or byte in this part of the message changes, the MIC would change. So you can only verify the MIC if nothing has changed, and you can only compute the MIC if you know the key. It also protects against replay thanks to a 2-byte frame counter. And the 2-byte frame counter is included in the MIC computation. Two more fields of the protocol overhead of the protocol signaling part is present in each frame. So one 4-byte field which tells the address of the device. This address identifies the device on this network, and the address includes as a header the network ID. So it's a network ID and device address on that network, having a network ID, and this part is not encrypted. So any gateway, any network that receives a frame, if the network ID field is not a match with that network, it can still try to forward or sell that message to another network server that will be interested by this message. So this is the basics of roaming. You get a message from the address, which is in the message, you know its destination, therefore you can forward it to the right place. There are also 3 bytes of link control, which give the type of frame, also the type of traffic, the type of payload, and some bits that are there to check link quality regularly, and also to manage the acknowledgements, and also some traffic control. For instance, there's a bit which means there is pending traffic for you, dear end device, please open reception window so that I can send you that traffic. So again, that's the reason why the protocol is power efficient. Only 13 bytes are appended to each frame, and these 13 bytes include addressing, so networking, and all the security, so authentication, integrity protection, and protection versus replay. There is no need for time synchronization. The end devices transmit whenever they need to, whenever they want to, and they just listen briefly after each transmission for downlinks, which limits the power consumption allocated to downlinks, and we'll see that in the next slide. And end device stays connected without specific signaling. So this means that most of the energy allocated to a LoRaWAN operation is actually spent to transmit useful data, even when the device transmits a few tens of bytes per day. That's really why the protocol is optimized for low data rate devices, and the power is very efficient in this case. Of course, it's still as efficient when more data rate is transmitted, but the difficulty is to have something efficient when very, very few bytes per day may be sent. So now downlinks. How do we make downlinks available and keep the protocol power efficient? So the trick is that for each uplink, the end device will open downlink opportunities, so 2 downlink opportunities in the case of LoRaWAN are open after each uplink. These opportunities are very short. They are much shorter than the uplink packet, and also the average power consumption in reception mode is typically 5 times lower, and up to 50. Well, it can be even more, even lower, depending on the transmit power. And so the reception power is much lower than the transmit power. So all the combination of these two makes a very low add-on to the power budget of these 2 downlink opportunities. It's less than 5% of the power, even in regions where the transmit power is fairly low. So here, there is a frame. So this yellow, so green is still the encrypted payload. This is the message integrity check, and these are the bytes, the signaling bytes of the protocol, the address, the counter, and the flags, type, etc. flags. And this is in blue, the physical layer header, the LoRa header, which is there for synchronization and also signaling the length of the packet. And then you also a CRC to verify that the frame is complete. And here, this uplink is sent. The device opens 2 reception windows, but there is no signal. So between these 2 windows, between the transmission and the windows, and after the window, the device is in sleep mode where the power consumption is very low. Only there is the device active, and there active in reception. Then comes the next transmit frame. The first reception window is open but yields no detection. And the second reception window gets a detection. So you see it's not perfectly synchronized in frequency, not perfectly synchronized in time, but still the signal is detected. and the reception goes on until the end of the packet, and then the link is then completely received. So only when there is things to receive is the end device keeping its reception active. In addition to that, because of course the limitation of class A is that the latency of the downlink is unknown, is unpredictable. It depends on the end device sending an uplink. So if the end device doesn't send an uplink, you cannot reach it in the downlink. So to solve that limitation against additional power consumption, we have designed class B and class C. So class B is class A plus regular downlink opportunities thanks to time synchronization. So the end device will open multiple such reception windows, downlink opportunities, based on a grid, and therefore that's why we need time synchronization. And the number of these additional reception windows is class B in class B are between 1 per 2 minutes and 1 per second. So if you keep it at 1 per minute, the additional power consumption can be as low as 25%, and of course, if you increase, it can be more than one. It can be up to 100% or more. Class C is class A plus continuous reception. So you can hear that class B and class C are not compatible. It's either A plus B or A plus C, or A alone. And class C is continuous reception whenever the device is not transmitting. So that's reserved for mains power end devices, or it can be activated for a brief period of time, temporary activation, for instance, to do a firmware upgrade over the air. So devices can be in a multicast group that will transport the firmware update, and the network will tell them to turn on for 1 hour, half an hour, whatever time is required for the FLOTA packets to be received. So now I'm going to talk about the collaborative network topology of LoRaWAN, and the main advantage is better coverage. So first, on the left is not a LoRaWAN topology, is a traditional, I would say, cellular network topology. Cellular like in cell phones, 2G, 3G, 4G, etc., 5G. And in a cellular network topology, base stations do not share resources with their neighbors. So cells are defined, and if that cell is using frequency resources, for instance, second set of frequencies, F2, its neighbors, the adjacent cells, will not use the same resources to avoid interference. The situation is a little bit the same with Wi-Fi networks. For instance, at 2.4 gigahertz, Wi-Fi 2.4 only has 3 non-overlapping channels, and typically you would pick up a different channel than your neighbors, because you probably know that Wi-Fi better coexist when different resources are allocated to different networks. So that's not cellular because it's not planned as a cellular network, but resources are kept distinct. In a collaborative network, it's the almost complete opposite when it comes to resource sharing, because every gateway is trying to receive packets on all available channels, on all channels defined in the network. So this has multiple advantages. The first one is better coverage, thanks to diversity. We call it macro diversity, because you have more chances of being in reach of a gateway if all the gateways may be listening to you, of course. And it's important because in IoT, devices cannot move. Even if they are mobile, they don't choose their location. When we are on the phone, we can decide to move a little bit to have better coverage, but that's not an option for a water meter, for instance. The connectivity needs to be good where the meter is. So that's good for coverage. That's also good for interference. And we are using license exempt band, meaning that we share the spectrum with other users. So our signal is perceived to the others as interference, and signals from other technologies are also perceived by LoRaWAN networks as interference. So diversity in the resources, so in the channels, in the frequency channels, is also good to better mitigate the interference. And it's also good to be a better neighbor to the other network technologies. Also, because the coverage is better, so hard-to-reach nodes are better served, but also nodes which are well served are even better served thanks to redundancy. They can be, if a node is outdoors, it will typically be received by multiple gateways. Therefore, that node, which is in good condition, can increase its data rate, therefore reduce the time spent to send packets, which reduces the power consumption, because again, most of the power consumption is allocated to transmit data. So if the transmission is faster, the power consumption is lower. The other advantage of having such a collaborative network is there is no association to a particular gateway. So here is on the protocol side, the end device is not attached to a gateway. It's connected to the entire set of gateways, and even the gateways which is very far from, any gateway from the network will relay the frames of the device. The device is always connected, and that saves a lot of power because there's no signaling associated to keeping up to date with a particular gateway, negotiating a change of cell. So this does not happen because a device is not connected to a particular gateway. Another advantage is that, so here we can imagine that it's the same network where gateways share coverage, but you can imagine that several networks also use the same channels, and which improve coverage globally because networks can collaborate. And from the point of view of the end device, this is seamless. The end device doesn't realize that it's been relayed by network A, by a network A gateway, or by a network B gateway. For the end device, it doesn't matter. Coverage again, because this is a very difficult problem of IoT. So in LoRaWAN, there are multiple levers to optimize coverage. And it's very important that the network server, because that's the role of the network server, uses well these levers. And the levers are called adaptive data rate. So these are commands to change the data rate and transmit power and repetition order of transmission. Repetition order is the way LoRaWAN uses to get frequency diversity. So having different channel realization because the frequency changes. Macro diversity is also a lever in LoRaWAN, thanks to the gateway listening to same channels. And last, acknowledgements is also a way to make sure that the frame has been received correctly. By the way, this is the only way to make sure that the frame has been received correctly. Acknowledgements, feedback is the only way to be sure someone received your message. So here's an example of proper use of all these levers. So this is an example where the channel propagation is non-line of sight, meaning that it results in relay fading, meaning huge variation in the signal power. So for instance, for an average, if the average signal level here on the x-axis is minus 130 dBm, so that's the average, but some frames will experience much lower, typically 15 dB lower, down to 15 dB lower, and some frames will experience much higher, typically 15 dB higher also. So here we report the average RSSI. So keep in mind that there is a huge variation around that. And for this average RSSI, the network server optimizes the data rate and retransmission order of the device. And here in blue is the data rate, so that we called spreading factor in LoRaWAN, but A high spreading factor means a low data rate, 12, 11, 10, up to 7, and also 6 and 5. So these are new data rates that will be published soon in the regional parameters when the next version of the next release of the regional parameters document is published. So as the data rate is increased, the time on air is reduced gradually, and it's reduced in a gradual manner, not with steps, and that's because repetitions happen. So again, frequency diversity is about, in LoRaWAN, repeating the same frame at different frequencies to experience different channel conditions. It's a way to put its eggs in different baskets. So the baskets are the channels. And effectively, the repetition of this way, here is a case where the network is going to actively acknowledge every transmission. That's a way to reduce the number of transmission, which is between 2 and 3, as you can see. So on average, a frame is going to be transmitted 2, 2.5, or 3 times. And that's thanks to the acknowledgement. If the network doesn't feel like sending acknowledgements or is not configured to do so, the number of transmitted frames will be slightly higher, probably between 4 and 5, because to be sure, to increase the certainty of reception, there's going to be a little bit of waste of transmission, a blind transmission in the absence of feedback. But with this feedback, the number of retransmission is fairly low, limited to 3. So yes, next thing. So this was coverage optimization with the baseline of LoRaWAN, but we also have expansion of coverage thanks to 2 things, satellites and low power relay. I'll start with the satellites briefly. So we have support for LEO, low Earth orbit satellites, so satellites which are only 500 to 800 kilometers high, and geostationary satellites which are much higher, 36,000 kilometers high or distant from the ground. And with LoRaWAN and the dedicated data rate and physical layer, we can have direct connectivity to satellites because of the long range and still at a low transmitted power and reasonable time on air, meaning that it's still long range. So in that case, it's very long range and still low power. It uses either ISM bands, typically the LEO case uses ISM bands, or licensed bands, and typically the geostationary satellites use licensed bands. We need satellites because in many areas, terrestrial networks are just not viable economically. It's too expensive to set up gateways, either because the place is a kind of desert, like a blue, green, or sand desert, but it also sometimes when you want to cover a line, sensors which are along a line, like a railway, a pipeline, an electric line, whatever, again, is arranged in lines. Whenever you set up coverage with gateways, a gateway is covering an area, and an area to cover a line is a waste of gateway resources, therefore gateway installation costs and so on. And in that case, satellites happen to be a very viable option. We also added a low power relay. So low power relay means it can be battery operated or it can be energy harvesting operated. And that relay is a coverage expansion to address a few devices which are very, very hard to reach. Between the device that is relayed and the relay, there is a special protocol which uses LoRa in a special mode that we call wake-on radio. And it's a mode where the relay is constantly reachable with some delay. Not constantly reachable without delay, and still consumes a little bit of energy and can last a long time on battery or last forever on energy harvesting. So I'm going to conclude the talk with upcoming features in LoRaWAN. These are not ranked in any kind of order, just a list. So the top of the list is plug and play. So we're working on making device activation as simple as scanning a QR code. You have a device, you take it out of the box, install it where it needs to be, scan its QR code, and off you go. The device is activated on the network, its profile is known to the network, the codec is downloaded in the application server, the credentials are distributed wherever they need to be, the device is claimed, the network knows that you own the device. So it's the equivalent of inserting a SIM card, but then you just flash a QR code. We work also on standard network server to gateway interface. So we have interfaces, obviously, because the network exists with many gateways and 100 million devices. So there is an interface, it's just not standard yet, so we're making it standard, so it's easier to install and scale. We will be adding asymmetric cryptography to simplify keys provisioning. So remember that root key, the red one in the beginning of the presentation. So it needs to be stored in the end device securely, and adding asymmetric cryptography, meaning certificates instead of symmetric, well, to generate the symmetric cryptography is a way to simplify provisioning during manufacturing deployment. It's not making it more secure, it's just making it simpler. We also work on drive-by operation. This is supported by the definition of a beacon, which will be received in a low power manner. That beacon is going to describe some capabilities of gateways or networks. So it's a low power network discovery principle. This low power network discovery is really low power. The power consumption on the end device can be made hardly noticeable, and still the end device will be kind of permanently able to receive any beacon from any network. So should it be a mobile network driving by, so van driving by to collect metering information. Drive-by is really a market demand from the metering industry. It can also allow an end device to discover its node at home and can transmit more data because it arrived at destination. It also enables collaboration between networks. For instance, you can imagine that a Sigfox network, say, sends a beacon telling, there is a Sigfox network available here. So if you don't have LoRaWAN coverage, consider changing to my network. It's a way to enable network collaboration because this network discovery is low power and it can be permanently on. Last on this list is the activity, which is pretty high, pretty strong in satellites. So there are already commercial services, but we are still working on elements to improve the solution. So we're going to publish a regional channel plan for satellites. So that will be in an upcoming version of the regional parameters document specification. We're also going to publish a LoRaWAN over satellite specification. So how to best use LoRaWAN when satellite is the link. And we also have, and that's not shown here, a strong regulatory support from our regulatory working group to ensure that satellites keep access to ISM spectrum and also are able to use it on the downlink, so from the satellite to the ground, making sure, of course, that coexistence with other systems is ideal, is perfect. Well, but keep open this opportunity for satellites, typically LEO satellites operating in sub-gigahertz bands, to send downlinks to any device, and that again, it's a direct satellite to end device connection. So this is the end of this part of the presentation, and we can now go to the Q&A part. A good list of questions already. The first question is on AS128. Someone says it's not safe, it's not state of the art. What do I need to do if I need better security? Can I implement my encryption? So it is actually state of the art, and I'm going to no, okay, done. send. Okay, I will do that. Yeah. I'm typing an answer because that's in my bookmarks. The question has disappeared. Okay, so there is actually a NIST FAQ on security that tells that AS128 is secure for the decades to come. So if you look this up, it's about post-quantum cryptography, and so again the NIST, this US-based organization, considers that AS128 is good for many years to come still. But if you do want to use a different cipher suite, that's going to be possible starting with LoRaWAN version 1.2.0, where different cryptographic primitives can be used. There will be need to be defined, and because the whole set of primitives needs to be modified. But you can propose one. You can come to the LoRa Alliance, join the LoRa Alliance, and propose the cipher you desire to use instead of AS128. There was then a question of what are the benefits of LoRa Alliance membership for solution makers who intend to rely only on LoRa modulation, but not on the LoRaWAN radio network standard? So the answer is fairly simple. Well, you should definitely consider using LoRaWAN unless you want to reinvent everything. And if something does not fit your needs in LoRaWAN, well, we can change it, we can update it, we can upgrade it. With that, we add options whenever this is required by the market. Next question by Subhash is on compliance with security and certifications or standards. So this compliance is typically the responsibility of the device manufacturer or the network operator. The LoRa Alliance can only do its part, which is making sure that products that incorporate the LoRaWAN protocol, because the LoRaWAN protocol is only a part of that product that incorporates this protocol can be made certified with against this certification or standards. Recent standards, recent directives in Europe, for instance, the RED directive or the CRA directive, they have different requirements that apply to different type of end devices. So it's really end device dependent, the kind of certification which is required. Then a question from Thomas on interference management. How does that work with LoRaWAN network? And then a follow-up question, more specifically, elevated noise floor ambient environments. So high noise floor and interference are not exactly the same thing. High noise floor means constant noise, and interference tends to be bursted, specifically in unlicensed bands where regulation impose that transmission don't last forever. So this said, some channels happen to be more used than others, and the first line of defense of mitigation versus interference is to not use that channel. The LoRaWAN protocol is capable of configuring dynamically the channel plan for all devices which are served by a set of gateways. That's a way to avoid the worst channels. Then there is, if every channel has a higher noise level, this happens in very, very crowded places, then the adaptive data rate is going to effectively pick up the best data rate to have reliable communication. There is this range of data rates is good also for that. Next question also by Subhash. Will networks like Starlink making data and communication cheaper and pervasive with networks like Starlink making data and communication cheaper and pervasive? Do we foresee difficult times ahead for LP1 and specifically LoRa or LoRaWAN? So I don't think so. I don't think we compete with Starlink or that Starlink competes with LoRaWAN networks. The difference is on the power consumption of the end device. I don't know of Starlink endpoints that can be battery operated or operated by the on energy harvesting. And LoRaWAN, of course, is not addressing at all the same range of data rates. Next question from Sade. What is the disadvantage for the LoRaWAN? So I'm not here to talk about the disadvantage of LoRaWAN, but I can tell about the limits. Again, it's really designed and optimized for low data rate, infrequent, short transmission of uplink or downlink, well, from data from the end devices or to the end devices. There's no practical limit on capacity. Really, the protocol, as long as the devices are used in this way, meaning sparse transmissions. Question from David. When is 1.2.0 coming out? So I am the editor of that spec. It should be coming out along with reference implementation and certification program. So all in that package, 3 things. So even more things. So the spec, stack, the LCTT, and the certification program. And that, so we're working on it. And I hope that we will be publishing this at the beginning of next year. Next question from Rogers or Don. Sorry about mixing up the name and surname. Can you elaborate on how the drive-by network will work? So the drive-by network will work in polling mode. The van, the moving gateway, will signal its presence with a beacon. That beacon will be received in a very low power manner, meaning that all the end devices will permanently be looking for that beacon, and that permanent reception of the beacon will be low power because it will use a very, very low duty cycle, typically less than 1%, down to 1 per 1,000. So with 1 per 1,000 reception time, so 1 second every 1,000 seconds, or 1 millisecond every second, actually. That's going to be the duty cycle. The device is always reachable with that beacon. And whenever a beacon comes in, pops up, the device will know that it's time to transmit its data to the nearby gateway. What is next question from an anonymous Anthony? What is the status of the pending EU Cyber Resilience Act? So the LoRa Alliance is not responsible for that. It's a European regulation, and this regulation is going to come into force, I think, in 2 years from now, and people will have to follow it. LoRaWAN is for its part will be compliant with it. Then another question from David: what are the maximum and minimum data rate? The maximum data rates that LoRaWAN can achieve. So the maximum data rate is 50 kilobit per second using FSK. How can LoRaWAN help in logistics is the next question. So LoRaWAN can help in logistics with trackers, with some trackers can be as small as stickers you put on things you want to track. There are very low power GPS available that can be part of the tracker. So and sending the position. That's the trackers we see in logistics. Logistics is one of the big verticals that LoRaWAN addresses. The next question is from Sandeep. Can we get certified, and how to get it, or how to get detailed training? So we're going to work on that, add more training within the alliance or recommend trainings from third parties within the alliance. So questions are adding faster than I can answer them. I will have to end at some point. Can LoRaWAN be used underwater? Question from David. In the ocean, saltwater for submersives? I don't think so. LoRaWAN is used just over the water surface, just over the ocean. That's actually how we had our record of distance from a buoy to a gateway on an island, 1,400 kilometers away. But in the ocean, especially with salty water, propagation of radio waves is really, really, really bad. So it will not go very far. How does LoRaWAN enable bidirectional communication while maintaining low power usage? So it's by opening very, very short reception window after each uplink message. So it's always the same principle, having a low reception duty cycle. So here, it's not even a duty cycle, it's two downlink opportunities after each uplink that allows the lowest power consumption. So next question, David. Will version 1.2.0 be backward compatible with version 1.1? Yes, it will, though version 1.1 is not very much deployed. The dominant version now is version 1.0.4, but all versions are compatible. What is the difference between LoRa and LoRaWAN? So I will say it again. LoRa is the physical layer, it's the radio modulation, it's a point-to-point technology, and LoRaWAN is a networking technology that uses radio links. So point to multi-point, and a protocol that tells how devices that use LoRa behave in such a network. Question from Fabian. Could you explain again why LoRaWAN will never be replaced by Starlink or similar satellite systems? So first of all, never say never. But the thing is, we really don't try to optimize for throughput. We don't try to optimize for cost per transmitted or received bit. That's not the play. That's not the problem we're solving with LoRaWAN. What we're solving is connectivity with very, very low energy. And high data rate doesn't go well with low energy. So if you optimize for high data rate, broadband, you will not optimize for low energy. That's the two are just incompatible. So we have optimized for low power operation down to energy harvesting operation. So that's what we do. Also, long range doesn't go with doesn't go well with low power unless you reduce the data rate. So to have long range, we reduce the data rate. So I think we get to the last question, and thank you for staying till the end. From Dominique. How is the LoRaWAN covering Africa region? Then could we get the recording after the call? Yes, you will get the recording and the slides after the call. That will be available to all people who are registered to the webinar. So is LoRaWAN covering Africa region? So the LoRa Alliance is not responsible to set up networks, but we know that there are several public networks and many, many private networks in Africa countries. Also, since there are satellite services which are commercial, the satellites, so the LEO satellites, they rotate over the Earth. So they pass over every place on the planet. So every place on the planet is at least covered by the LEO constellation that operate LoRaWAN. Okay, so that's the end of your questions. Thanks again for this active participation in the webinar, and sorry for the limited interaction. But I hope you had a good time and learned a few things on LoRaWAN. Thank you. Bye-bye.